Another example for class 22. Here are problems 64, 65, and 66 from Borgnacki. It's good I like doing this where you have, I don't like doing it. And I think it's good practice to do this compare and contrast when you have all this information that's presented to you, so you can try to organize your brain and see the variations. What's the difference between an adiabatic process, an isothermal process, and a polytropic process, all for the same gas, where we start out with 100 kilopascals and 300 degrees Kelvin, and then we compress it to 800 kilopascals. In this case, is 1 kilogram of propane gas. So we want to find the work required for this if it's adiabatic, right? So first we'll go to our properties up here. And let me delete that one. And let me delete that one. Here's propane down here. Boom, 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 boom. So let's write all those down. So we say table A5, and R is 0.1886. I'm going to leave off the units and write CP 1.679. I probably don't need that. CV probably do need that. Maybe not. I don't know. 1.490, and there's a K, and we don't necessarily need it for this one. Yeah, no, I think we do. Anyway, let's see. Okay, so I wrote all of them down, and should put units on everything just to be complete. Even though I didn't leave enough room. There you go. And they say it's adiabatic. The question is it isentropic? Well, I'm going to have to admit that I know that it's possible to have something that's adiabatic that's not isentropic, but it ain't very often, right? So what we know that means is that Q doesn't change for the adiabatic setup. It equals 0. And we also know that kind of a definition equation of entropy is to have the change in heat, the heat change. And so therefore, we'll say this isentropic. If they had said it was adiabatic and reversible, it would have been isentropic. But they didn't say those words. So that's why I'm bothering even bringing that up. So let's use isentropic. We know that U2 minus U1 is equal to Q1 to 2 minus work 1 to 2, but it's isentropic right here. So we could find what the work is going to be if, and this would be like when we put negative, because the negative is going to go over there, negative U2 plus U1. And so maybe I could just put that right here. I'll go to MC, that's U, so that's CV, T2 minus T1. So we were given T1, right? So I should write down the things that we know. T1 is equal to 300 degrees Kelvin. P1 is 100 kilopascals. And P2 is 800 kilopascals. And in the previous class, you'll recall we did for isentropic. So we wanted to point out that we don't know T2 yet, but we can find T2 because we already have the equations from the previous class. Did I put those away? What did I do with those? Yeah, I probably did. I have the cheat sheet here. I could look at the cheat sheet. Let's look at the cheat sheet. Isentropic process, or we could look at our equations here. So we have an isentropic process, and we could find T2 from P2 over P1. So we have T2 is equal to T1, P2 over P1 raised to the K minus 1 over K, right? Even though in this class we've been doing polytropic process, we probably see the same equation, but that's right. So we'll write this out as T2 is equal to T1 times P2 over P1 raised to the K minus 1 over K. So that's 300 times 800, right, P2, over 100, and raised to the 1.126 minus 1 over the 1.126. If we do that, we end up finding 378.6. Not a lot of difference right there. Went from 300 to 378.6, but we can see it's a lot of it has to do with the how small that is. And if we do that, we get a work between 1 and 2 of negative 117.1 kilojoules, right? I'm sorry, I didn't write out the thing. I didn't write it out. Damn it. Right, so we go back up to here and go work 1 to 2 is equal to negative the mass is 1, right? That doesn't really help us all that much. Okay, but it changes what the units are. CV, which is the 1.490, and then 378.6 minus 300, and we end up with and I'll just write it here as negative, and I wrote the number down already, 117.1 kilojoules. Bump, bump. Okay. Now let's do, so that right there was problem 646. Now, 664, 665. Do the same problem, but make it a process isothermal, right? So here's 665. And all of, okay, so this temperature is not going to be 378.6. It's going to be 300 because it's isothermal, right? So the isothermal. And we already have an equation for that from our previous notes right here. Let's see. I messed them all up right here. But here's our notes where we went through and we found work in a whole bunch of different ways. But here's one with okay, so here's the temperature right here, and here's the two pressures right there. So we this is going to be the one that's going to be useful to us, right? We have work 1 to 2. It's going to equal to mRT. The temperature is the constant P1. So that's the one that we're going to use. The isothermal process. Work 1 to 2 is going to be equal to mRT natural log, and I think this natural log will give you the same values depending on you go P2 over P1, but this is going to be P1 over P2, right? It's just going to change the sign, right? So, but the signs are important to us. We notice 1 times R, which was 0.1886, T, which is 300, and then the natural log of, I think we're 100 over 800, right? Is that true? Yes. And the work between those two states, we end up finding that it's going to be a negative 117.6 kilojoules. Compare that to this one, right? It's slightly different. We took a different path, right? This is an isothermal path. This is an isentropic path to be going on there. It's interesting how close they are, though. And then we're going to go 666, root 66. We're going to have a polytropic process where N is equal to 1.25, which, by the way, is larger than K. So 1.25, you're saying to do that. And so we have this work, the equation for the work. Easiest thing for us to do maybe is to do this version of the work equation. went the long way around in describing that, I think, yeah, in the beginning for the polytropic process, right? I said we had this one, but it also equals this one. This is going to be easier for us because we could find what the temperature 2 is going to be. Otherwise, we had to find out what the volumes are going to be. So we won't need this. No, we have the M. So this is the one we're going to write down. M times R times the change in temperature over 1 minus the exponent. So we're going to go M R T2 minus T1 over 1 minus N. But we need that T2 first, right? Because that's not going to be the same T2 as up here. This is a T2 that was based on isentropic. We're going to have T2 is equal to T1 times P. Let's look it up. I don't want to. I mean, it's the same as we kind of did up above, but don't worry about it. Let's go for the polytropic, and we see that we're going to have we need T, right? So we need T2 is going to be equal to T1 P2 over P1 raised to the n minus 1 over n. So yes, that's the one that we need. So we go. I just had a second ago. Your brain is so slow. P2 over P1 raised to the n minus 1 over n. So that's 300. And once again, we're going to have 800 over 100. And now it's going to be 1.25 minus 1 over 1.25. And we'll get a T2 of 454.7 degrees Kelvin. That's quite a bit difference between the isentropic right here, this polytropic one. But we'll put him back into here and get out the work. So we got 1 kilogram. We get our gas constant, which is 0.1886, and then 454.7 minus 300, all divided by 1 minus 1.25, right? So it's going to be a negative 0.25 in the denominator. So we're going to end up having a negative value of 116.7 kilojoules. Interesting thing to compare, don't you think? What's something that I did was also to find, we could find what the initial volume was from the ideal gas law from these two things. And then we could find, doing the ideal gas law for these others, you could find what the final velocity is with that pressure. And then on a PV diagram, I'm not going to bother with my TS diagram. I've always felt that TS diagram is not nearly as valuable, at least not to me, as the PV diagram. Because I've used these. We could actually measure pressure. We can actually measure volume, right? Especially in a gas turbine, not a gas turbine, especially in a diesel engine or a gasoline engine. You don't know what the volume is, and you can also get the specific volume if you know what the mass is. But as a physical thing, PV is actually pretty easy to find, and find what PV diagrams are, and then analyze the PV diagrams, compare them to what the idealized PV diagrams are. There's a lot of information to be gathered from here, but I digress. We are moving from one pressure to another pressure, right? And we're starting out in the same place, so we know where we're starting. And if we found the volumes of the 3 separate things, right? So we're going to have 3 different landing points, and when it turns out, when we go to the adiabatic isentropic process, we have all right, so we're going to start out here at 0.56, and we're going to go down on the adiabatic process of 0.09, let's say, 0.09, which is kind of like in the middle of these 3, right? Because when we go to isothermal, this is actually 0.07 or 0.08. And then when we are polytropic, we're actually up here at like 0.1, right? So we have the largest one of the polytropic, so you kind of go up to there, and then the isentropic was kind of like right to there, and then the isothermal was kind of like right to there, right? So these were the different landing spots. They all had the same pressure of 800 kilopascals, but the path was slightly different. And then that's kind of explains in some respects, but not all, where you have the most amount of work right here. You went the furthest addition down here. So work is the area underneath the PV diagram. Can I say that? I think so. Polytropic, I said, was right here. Okay. But it's also the path that it takes, right? The amount of curvature that it's actually taking. It dips into, right? Well, a lot of times what we did earlier on in the semester was to have like a trapezoid type of thing going on here. Well, that's going to be different, right? If you do a straight line right in there. And that was all done with like a spring, right? I'm going to say we forced it because that's like a pun, but we did try to make it. We put an external influence onto it, which was the spring that ensured that it was going to be a linear line that was being drawn from one stop to another as we were moving from a volume to a volume and a pressure to a pressure. The force had to be linear because the area was constant and the force was constant, or the force was changing in a linear way, and therefore it had to be a straight line. But here we are defining a processes not based on some external thing of the spring, but an external of the way that we're treating it. One is going to be isothermal, so we made sure the temperature had to be the same all the way through that process. Or isentropic, we made sure that it was that no heat was being exchanged. And then the polytropic, you can think of that more of we were just describing how it got done, right? So we'll do another couple examples after this.